Okay, I want to summarize a paper. I think it's a very important paper that we published in International Journal of Neonatal Screening by Robinson and Gelb. It came out this year in 2019, and it has to do with imprecision at the screen cutoff. You can find it online. It's free. Go to the International Journal Neonatal Screening website. Now, I think it's a must-read paper for anybody in newborn screening. It covers very nicely the statistics of newborn screening and cutoffs in a rigorous way. The paper was read by two professors of statistics at the University of Washington, and my colleague Bruce Robinson is a mathematically inclined theoretical physical chemist, and he knows his way around statistics. And I think when you see the results, you'll be convinced that they're spot on. Now, I mean, what the paper kind of gets at is, what is it about the assay that's most important for determining the number of false positives and false negatives? And I'm going to focus mostly on false positives, and let me just tell you the answer, and maybe it'll make sense immediately. Maybe you would say it's obvious this is true, and it turns out that you know. Cutoffs tend to be at the lower end of the enzyme activity that you find in populations. 7% for MPS 1, 7% of mean activity for MPS 1, 5% for Pompe if you're, 15% for Pompe if you're using mass spec, 25% of mean if you're using digital microfluidics. The difference is due to what I said in my last tutorial. But these are low amounts of activity, and so we really don't care much about how the assay behaves in terms of its imprecision performance at activities around 80% of normal, 100%, because nobody with the disease is anywhere close to those kinds of activities. All of the action in newborn screening happens at the low end. The cutoffs are very low compared to the population mean. And it turns out that the imprecision in the action region near the cutoff is what determines the rate of false positives and false negatives. And said another way, let's say all of the imprecision of the assay was focused down at the low end. Maybe the assay is perfectly precise at the cutoff, way above the cutoff. Maybe it falls apart in precision at 3% of mean activity or lower, but not at the cutoff. And we really don't care that the assay doesn't do very well in terms of statistical behavior, in terms of reproducibility at the very low end, because the cutoff is way above that. We really don't care if the baby has 3% activity or 5%. They're both going to be screen positive if the cutoff is 10%, right? Right, so it's pretty clear that it's the imprecision at the cutoff that matters. Now, you might think that if you have an assay that gives a higher micromole per liter, per hour per liter than another assay for a given sample, that the one that has the higher enzyme activity would be the better assay for reducing the number of false positives and false negatives. But that is completely not true. You could have an assay that gives a relatively low micromole per hour per liter for any given sample compared to another assay. But if that assay is more reproducible, if it's more precise at the cutoff, it will outperform the assay that has the higher absolute activity but the lower imprecision at the cutoff. Okay? I mean, one assay says 12 micromoles per liter per hour on the same sample. The other assay says 20 micromoles per liter per hour. That's not what determines the the rate of false positives and negatives. It's really the reproducibility, the precision, or the imprecision of the assay at the cutoff that matters. All right, so it kind of makes sense that this is true. This is kind of what your logic would say, simple logic. And in this paper, we actually prove that this is the case in a rigorous mathematical way. Without going through the whole paper, let me give you a little bit of insight into the statistical analysis. Okay. Let me start with distributions of activities, distributions of enzyme activities. Or, this doesn't have to be enzyme activities. It could be biomarker concentrations. But let's focus on enzyme activities as an example. It doesn't really matter. It could be cytosine concentration. So let's say we screen 100,000 newborns using some platform, mass spec, for example, and we plot the population distribution of the activities. Well, the way we do this is we do it by binning. We might say, well, we have 100,000 newborns, and 25 of them have enzyme activity in the 1 to 1.5 micromoles per hour per liter range. We have 70 in the 1.5 to 2 range, whatever. So we assign some bins, and we ask how many newborns are in those bins. And to normalize it, let's divide the number of newborns in the bin by the number of newborns screened, which is 100,000. So here, for example, this is the bin corresponding to 1 to 1.5, and here's the bar graph. So this number would be 25 over 100,000. All right, and so you get a series of bins, each one with a bar, and you plot these out. And you've seen these plots before. You get some sort of bell-shaped curve. Okay, you get a bar for each bin, and looks something like this. And you can draw a curve through the top of these bars and get some sort of smooth function. All right, and let's talk about what this function typically looks like. I should say that these are often called probability distribution functions. Why probability? I mean, this is actually based on actual data. How many babies in this bin did we see? 25 divided by 100,000. But if you were to do this on the next baby in the future, well, what is the probability that this baby is in this bin? Well, depends on this number. Okay, so this axis you could on the 100,000 data set is how many babies are in that bin divided by 100,000, or you could also say for the future, what is the probability of finding a baby in that bin? Well, it's the same number. So in that sense, this is the probability distribution function, okay? And that's how it works in statistics, and you understand that. All right, now let's look at the shape of these distribution functions. You might expect, like most things in populations, to be some sort of Gaussian shape, some sort of bell-shaped curve, or normal distribution. That's something like this. And you have some mean value, the most common, the highest probability bin, and then, less and less babies are below that, and it tails off to 0 in both directions. And most of the time, these things are symmetrical. That is, the area on one side is the same as the area on the other side. But one thing you need to remember that, let's say this is 0, the bin for 0 enzyme activity. It's kind of impossible to have any newborn that has negative enzyme activity. Well, it's not quite true because there's error in the assay, and the observed assay response for the newborn could be less than that of the blank, and you could have experimentally a negative activity. But that's a small effect. So we expect we're not going to have a lot of babies way down here at negative big number. They're going to have to go somewhere. They can't go too far to the left of 0 along the x-axis. All right. So if the mean is far to the right of 0 compared to the width of this distribution, let's say the half width, you expect to see a nice symmetrical distribution where this tail reaches 0 before we collide with the origin, and likewise here. But if the mean starts to move towards 0, if the distance from 0 to the mean is comparable to the width of the distribution, there has to be a skewing so that it tails more to the right of the mean than to the left, because we can't go into this region of negative activity. So this is no longer a normal distribution. This is called a log normal distribution. And this is what we see almost always in newborn screening results if we bin them across a population. Now you might say, is there anything fundamental about biology and enzyme activities that is appropriate for the mathematics of the log normal distribution? And the answer is not as far as anyone knows, not as far as I know. It's just that the log normal mathematical function is a simple, well-behaved function that well fits the population data in newborn screening. You know, it doesn't mean that biologically the activities strictly follow a log normal distribution. It means that this function well describes, well fits the data. There could be another function out there that's fundamentally not log normal that also well fits the function. It doesn't really matter. You could use that function in the mathematics of newborn screening. All you require is a well-behaved function that well fits the data, and the log normal almost always satisfies that condition. So we're going to fit the data to log normal, and that's good enough, right? All right. Now, let's consider the assay. And we measure some activity, micromole per hour per liter for some newborn number 1. So I'd like to say, well, there's the true answer, and there's what we measure. All right, there's a difference because of error. You know, the true answer might be 12.67, and we measure 13.92 because the measurement has error. Or we might measure it multiple times and we get different answers. And this explains why we don't exactly get the truth. Okay? This is called imprecision, right? Or error. And you all know this. This is the true answer. This is the error. Now, what do I mean by true answer? Well, you know, the blood spot is not perfect, right? The amount of blood per 3 millimeter punch might vary with the degree of saturation of paper. Maybe all the enzymes in the leukocytes, and the leukocytes don't spread evenly across the filter paper. So the blood spots, we all know, is not a perfect way to sample and measure the amount of enzyme in blood, right? There's some artifacts. But I want to take that off the table because I'm going to compare two assay platforms, let's say fluorescence versus mass spec, where both uses the same sample, dried blood spots. So in any comparison between these two, it can't be blood spots that's the difference because it's used in both, and so that's off the table. So that might be one reason why the measured activity is not equal to the true activity in the blood because of this sampling problem, but that's not what we're talking about here. When we compare these two platforms carried out on the same sample, that is the dried blood spots. So even if, so said another way, we could take the same sample and we could, we don't expect to get the same answer if we were to measure it multiple times because the assay has some imprecision, okay? And let's talk about imprecision not due to problems with the blood spot. Let's talk about imprecision due to problems with the assay itself, okay? The mass spec might be more precise than the fluorescence or vice versa. Nothing to do with blood spots. It has to do with the assay, the machine that measures the activity itself. All right, so how do we deal with imprecision? Well, so the way statisticians deal with this is to realize that we observe, this is the observed distribution, which is log normal. Well, I didn't draw it very well. It's a little more log normal. And this is the observed distribution. And really, what this is kind of a blend of the true values of the enzyme activity in the blood spot, blended somehow with the imprecision, okay? So in other words, maybe the true value of the enzyme activity in the blood spot is 12, but we measure 12.6 because of the imprecision. And when we measure 12.6, that's part of our observed distribution. So there's a relationship between the true distribution and the observed distribution, and that is called the convolution. The way you blend two probability distributions in statistics is to perform a mathematical operation called the convolution. I'm not going to go into it. So so what I'm trying to say is that the probability distribution that we observe is equal to the convolution between the probability distribution the true values of enzymes in the blood spots convoluted, given this symbol X with a circle, with the imprecision probability distribution due to imprecision. All right, so this is mathematically true. You can prove it, not today. So the real observed distribution that we see is a blend of the true distribution with convoluted with the imprecision. So if we knew what the imprecision distribution was, we could do the reciprocal of the convolution, which we know how to do mathematically, and obtain from the observed distribution the true distribution. Okay, we can do that if we know the imprecision distribution. You can prove that. So how do we measure the imprecision distribution? Well, the CDC does this for us. What the CDC does is they take multiple punches across their QC high standard, and they analyze it with mass spec 20 times from these 20 punches, and they plot it out, and they get some sort of distribution. Here's the mean activity. Here's the standard deviation, and this is in fact the probability distribution for the imprecision. So this is PDF for the imprecision. It's exactly what it is. And they can do the same thing for mass spec and digital microfluidics. Now, okay, if they take 20 different punches of the same blood spot, some of this distribution, some of this width is due to the fact that the amount of enzyme in all of the 20 punches is not exactly the same because of the blood spot sampling problem. But that's going to be true for digital microfluidics and mass spec to the same extent because it's the same sample. So if the assays themselves, the platforms, had zero imprecision, then we would expect some width to this curve due to just the blood spot itself, and the distribution for digital microfluidics and mass spec would be identical. But that's not the case. The CDC data shows that the imprecision in the digital microfluidics is higher than in mass spec, as published by the CDC. And the numbers are given in my review article written by 4 international authors. And it's the published data from the CDC as presented in the poster from the CDC at the New Orleans APHL meeting, and as published on the public newborn screening web portal from the CDC. All right. So we have the imprecision, but it's a little bit more complicated than that because the imprecision for the QC base, low, medium, and high, the width of this distribution could depend on which QC sample you use, right? There's no reason why the imprecision has to be the same on the instrument across all ranges of activity. In fact, they're not. And you can plot the standard deviation for the QC base, low, medium, and high for digital microfluidics and mass spec. And you get some curve, whatever. And so then if you want to estimate the imprecision at the assay cutoff, so let's say in digital microfluidics the assay cutoff is right here, you can estimate the imprecision by some sort of extrapolation, and you could do the same for mass spec. All right, so it turns out we can take the probability distribution function observed, and that's equal to the probability distribution function, the true one without imprecision equals 0, convoluted with the probability distribution function for the imprecision. Now it's a little bit more complicated because this distribution, this depends on the value of the activity, but mathematically we can do this numerically, and we can do this, and it's done in the paper, and out comes the probability distribution function if the imprecision in the assay platform were 0. Okay, so we can take the observed distribution that's been published for digital microfluidics and for mass spec, take the imprecision distributions that's published by the CDC, and we can obtain the probability distribution function if the imprecision in the assay platform were 0. That's interesting. Why is that interesting? What we can do then is we can calculate what the observed probability distribution would look like. Observed. So we have this probability distribution function if the imprecision is 0. I said we can get this mathematically. And now we can apply any probability distribution function we want for the imprecision. So we know this. We can provide this as an example. We can make it up, and we can obtain this. So now the game is very simple. So how does the probability distribution function observed, starting from here with zero imprecision, if we apply different types of imprecision? So for example, we might say that the assay is equally imprecise, has finite imprecision at all values of enzyme activity. Or we could say all of the imprecision is very close to the cutoff, and essentially none at very high enzyme activity, none at close to 0 enzyme activity. Or we can put all the imprecision at the high end, none at the cutoff, none at the low end. Do anything we want, and we did that in this paper. So then we need a way to score the number of false negatives and false positives. So let me just focus on false positives. All right, and this is going to be additional false positives caused by finite imprecision in the assay platform. So let's think about this for a minute. So here's our probability distribution function with imprecision equals 0. Here's our cutoff. And we can ask what happens to the distribution when the imprecision is not 0 in relationship to the cutoff. And again, we can do this by applying imprecision in different zones of enzyme activity. All right, so what's going to happen is this curve is going to broaden as we apply imprecision. And let's think about what broadening would do. Let's think about what broadening would do. Let's think about it non-mathematically, just in a very simple way. So So suppose your cutoff is 12 micromoles per hour per liter, and you get a newborn who's 14. So you would say this guy is above the cutoff, he's screen negative. But because of imprecision, maybe his activity is really 11. So you say 14, but it's really 11. And maybe this kid gets a disease because he's below the cutoff. And so this would be a false negative. Let's talk about false positives. You say the guy's 10, you measure 10, he's below the cutoff. The cutoff is 12. But because of the imprecision, he's really 13. So if you had no imprecision, he would be called screen negative, but because you have imprecision, you call him screen positive. He's a false positive. So, you win some, you lose some. Sometimes you read the enzyme above the cutoff, and the guy is really below the cutoff. Sometimes you read the enzyme below the cutoff, and he's really above the cutoff because of the imprecision. You win some, you lose some. The problem is the cutoff is always on the descending part of the distribution, right? It's always down here somewhere. It's never up here. So if you look at the distribution, there's just more people that are going to have enzyme activities just to the right of the cutoff than there are going to be people just below the cutoff. So more often you're going to have kids above the cutoff brought down below the cutoff by imprecision. Then you're going to have kids that are truly just below the cutoff that are brought high above the cutoff. And so you can see very easily that the more imprecision you have at the cutoff, you're going to increase the false positive rate. More often than not, you're going to have people above the cutoff that are truly screen negative, brought down below the cutoff because of the imprecision and told they are screen positive when they're not. You're going to have more of those guys than the other way around. And so you can read the paper, but this is a way to motivate the idea that imprecision at the cutoff will increase the false positive rate. You can play the same game if all the imprecision is way above the cutoff, and you'll see that this distribution doesn't broaden in this region, and so there's no effect on false positives. You can play the game where the imprecision is all focused way below the cutoff. They'll be broadening here, but not near the cutoff, and you won't increase the false positives. It's only when the imprecision is close to the cutoff do you increase the number of false positives by this imprecision broadening of the distribution. So this leads to a very important theorem that comes out of this paper, and you can read it, is that the most important assay parameter for our assay feature in comparing two different assay platforms, let's say fluorescence to mass spec, in determining who's going to have the higher false positives. It's not the absolute activities. So if fluorescence gives higher activities because they're in an optimal buffer compared to mass spec, that's not important. It's the imprecision at the cutoff. So the imprecision at the cutoff, not way above and not way below, is important at determining the rate of false positives. And so, said another way, the assay platform with the lowest imprecision at the cutoff will give the lowest rate of false positives. Now, if the two platforms measure different parameters, maybe one measures enzyme activity and one measures some biomarker concentration, one might give more false positives than the other. Nothing to do with imprecision. It just might be that biomarkers are better for newborn screening than enzyme activity. But if we're going to compare fluorescence enzyme activity to mass spec enzyme activity in dried blood spots, so both are doing enzyme activity. Both use the same sample. So those differences are off the, there's no difference there. That's off the table in the comparison. The only thing that matters in determining the rate of false positives is the imprecision of the assay platform at the cutoff. And this is important in newborn screening for LSTs because I remind you that for both techniques, mass spec and digital microfluidics, most of the screen positives are in fact false positives. So we care about the rate of false positives, the rate of, because, yeah. So maybe mass spec gives 20 false positives per 100,000, and maybe 19 of them. The mass spec gives 20 screen positives out of 100,000, and 19 of them are false positives. Maybe digital microfluidics gives 40 screen positives per 100,000. Maybe it gives 10, whatever. Most of those, too, are also false positives. So we care about the rate of false positives because it determines how much false alarms, how much follow-up, how much second-tier screening, how many phone calls we need to make. And we care about this a lot, right? And the only thing that really matters, if you compare enzyme activity across two platforms on the same sample, is the imprecision at the cutoff. Period. You can prove this as a theorem in statistics. It's mathematically rigorous. I mean, anybody that wants to challenge this needs to tell this team of statisticians what is wrong with this argument, because the mathematics dictates the answer. It is not subjective, as far as we can see. It is the final theorem, the final conclusion in this analysis, period.